Hi, everybody. Thanks for joining us. I'm Pasquale. I'm a software engineer at Facebook here in London.
And I'm Andy. I'm also a software engineer at Facebook.
So,
So for our presentation, we're going to be talking about threading on Android and specifically trying to demystify some of the primitives that Android uses to expose its threading abstractions, share some practical experiences that we've had with threading, and talk about using multiple threads for performance on Android.
so before we even start, just a side note on like why do we even need to use thread or in general parallel execution? Um, I'm sure you've heard before that threading is hard. It introduces bugs in your code that are hard to debug, and just in general, the code gets harder to read and write. So one obvious reason is, of course, that when you have some heavy work that you want to do in your application,
You're off.
I'm off. Yay. Cool. So think I'm off. We're still off. Yeah, great. So when you have some heavy work that you want to do in your application, say read data from a database or get data from the network or anything like that, you want to avoid doing this on the thread that handles the UI interface for your application, for obvious reason, because otherwise you would be giving a very bad experience to your users. The other reason why you might want to use threading, as Andy was mentioning, is that modern phones have multiple CPUs, which means that if you can parallelize your work across multiple threads, you actually can get better performances for your app. And in the specifics, you can make performance better in two ways. You can either try to move work ahead of time before you actually need it, say, to display some pieces of UI, or you can split your work into multiple pieces and therefore have each piece be done by different thread. Sorry.
So I'm going to show a diagram that many of you are probably familiar with, which is the UI thread on an Android device where you get a vsync every 16 milliseconds. And if you decide to do some heavy work somewhere in there, then you can miss one of these vsyncs. You miss drawing a frame. You end up skipping a frame, which makes your app feel janky. So one of the primary ways that we try to fix this is if we have a big contiguous block of work, we move it to the background thread and then have it communicate back to the UI thread when it's finished. And this allows the UI thread to be free to keep drawing frames. Android exposes a number of abstractions for communicating between threads. So you've got things like async task, intent service, and job scheduler. One of the cool things is that these are all just layers that are built on top of the same very simple threading primitive. So we're going to talk about those now. So the Android threading primitives are all based around this idea of a message queue. And a message queue is pretty simple. It's if you have a thread talking to another thread, it doesn't know what state that other thread is in. So when it tries to send a message, it needs to potentially be put into a queue to be processed whenever that thread has availability to process it. And this is the main primitive that Android uses for communicating between threads. The stuff that's built up around it, you have the handler, which is the thing that is responsible for putting items into that queue. The queue is hosted on a single thread and has a looper that's on it. And the looper is just a basic, like a while true loop that's draining that queue, processing each message. And when it processes the message, it goes back to the handler to actually dispatch whatever the message is supposed to do. So maybe it's a runnable that it does, or you can also have a message type where you switch on the message type and do something. So in this regard, the handler plays two roles, and it kind of allows you to namespace your different messages that can be run on the same thread. So for example, with the main thread that has a looper built into it, you can have different handlers that are all referencing that same looper that have their own namespaced messages that can be processed on the main thread.
So Andy mentioned that this primitive is actually quite simple. It's actually so simple that we'll just go through very quickly some of the pieces of code that are implemented in the Android OS to implement this. And you'll notice this is actually not very much. So let's start from Android thread. Android thread is a simple thread implementation that just exposes the concept of looper and message queue out of the box. So whenever you start a handler thread, what the handler thread does, it creates a looper by calling looper.prepare, and then it starts it by calling looper.loop. Oh wow, our dimming of code really dims. So what happens in prepare is actually not that, it's pretty simple as well. All the looper does, it creates a new looper and then it associates it with a thread local variable on that thread. And this is just a system made so that you can allocate handlers very easily, so handler can just go to the thread local and get the instance of the looper, and you are guaranteed that you only have one looper per thread. That is actually pretty important. And in terms of what the loop implementation does, as Andy mentioned, it just takes hold of the queue, it does a while true loop, and in this while true loop, just tries to get the next message out of the queue and dispatches the message to the target. Where the target, as said, is really just the handler itself. The handler implements two parts of the system. On one hand, it implements the dispatch message, where it decides to either run a runnable if the message callback is not null, or to just fall back on your subclass implementation for handle message. And then the other part is when you create the handler, as said, take holds on the looper on this thread. If this thread does not have a looper, it crashes, asking you to provide a looper, and it takes a hold of the queue on that looper. And then whenever you want to enqueue a message, all that this does is really put in a message on this queue that it took from the looper.
Great. So I'm going to give a couple examples of the abstractions that Android builds on top of this. So the first one is intent service, which is super simple. Whenever an intent comes into the service, it has its own service handler subclass that posts it to its message queue. Its message queue is just intents, and the looper just dispatches those intents back to the service handler, which then calls your on-handle intent. And then, I mean, the code for this, the code, if you look at intent service, is basically this. It's like 6 lines of code. It'll, whenever you get an intent, adds it to the queue, and then when it handles it, then it just calls your on-handle intent implementation. Async task is another example that uses these primitives where you have an executor for the do in background, and then whenever you're posting updated updates or the actual result, then it just is posting to that UI handler, which is putting in the UI's message queue, and the looper then dispatches that through the handler and calls your method.
Now you might be wondering, like, okay, these are all pretty old Android threading abstractions. Nowadays, we write our code in Kotlin. We use coroutines. So why should I care about any of this concept, and how do they apply to what we're doing today? So, I mean, if you look at literally the first line of documentation on coroutines on the Kotlin website, coroutines are essentially lightweight threads. So when you create a coroutine, you're creating a piece of code that is capable of running concurrently with other coroutines. You do not allocate a physical thread, but that's just because the parallelization is done by the language itself rather than the operating system. I mean, if you're not super familiar with coroutine, they're actually pretty simple to define. All you have to do is you use the launch function to define a piece of code that can execute concurrently with another piece of code. This code will print hello world in the right order, just because the coroutine will immediately go and delay its execution by a second. And since it's cooperative multitasking, I mean, what happens is that really the controller goes back to the UI thread immediately, that can print hello, and then it goes back to the coroutine that can print word. So pretty simple. Now, since coroutine are basically lightweight threads, they also present the same challenges that normal threads present, which means you do need a way to be able to communicate between coroutines in the same way that you want a way to communicate between threads. Turns out that the language itself provides pretty much the same mechanism. Coroutines expose this concept of channels. Now, channels are very similar to message queues. A channel is basically the queue in the examples that we were seeing earlier. And a coroutine can send a message on the channel, and another coroutine will get the message from the channel. And the coroutine that is getting the message from the channel basically does the same work that the looper was doing in the receiver thread, in the handler thread. Very simple example of channels. Again, very simple API, very nice to use. You just declare a channel. Within a coroutine, you can send messages to a channel, and then you can receive these messages either from another coroutine or just in your function scope. Now, what channels give us on top of normal message queues is that they give us a bunch of ways to handle back pressure automatically. Let's see a bit what this means. When you declare a channel, you can tell the channel how many messages it should handle. The very simple case is that you just tell the channel to be unlimited. If a channel is unlimited, it will behave exactly like a handler thread would. You can send as many messages as you want from like whichever coroutine or whichever thread, and these messages will just accumulate until the receiving coroutine like executes through them all. And of course, this is very nice because it doesn't block the sender. So for example, if you're sending from the UI thread, this is a very nice property. But on the other hand, the channel can grow indefinitely, which means that if the receiver cannot keep up, you can get a very, very long list of messages in this channel and eventually even crash for out of memory. So back pressure is actually a technique to avoid this from happening, where you want to make sure that like this is not a scenario that is, that will verify your app. Now, one simple way to implement back pressure is by saying to your channel that it has a buffer of a specific size. This means that the sender can send messages until the buffer is full, but then the moment the buffer gets full, then the sender tries to send another message, it will lock, exactly as the receiver would lock receiving messages from an empty channel. And this is, of course, very nice because now you have guarantees on the size of your queue, and you have guarantees that the receiver will never fall behind more than the size of your buffer number of messages. But this also means that the sender might end up blocking, which, depending on what you're trying to model, might not be ideal. Another way to implement back pressure is by using a conflated channel. What the conflated channel gives you is that the sender can send as many messages as it wants without blocking. But then what happens is that if there is already a message in the channel, instead of queuing them up, the message in the channel gets replaced by the message that the sender tries to send later. And this is nice because now the receiver has this very nice guarantee that only one message will be waiting in the channel, if any. But then again, you're also dropping messages, which might not be what you're trying to achieve. Last, there is another type of channel that you can use that is called rendezvous channel. And what the rendezvous channel does is that the sender will actually block immediately after sending a message until a receiver goes there and tries to receive that message, which gives you this property that the sender will not do any more work until the first message has been received, which may be ideal if the sender does very heavy operations, for example. But then at the same time, now you can not only block the receiver, but you can block the receiver and the sender, which is, again, depends on what you're trying to model.
Great. So we've covered some different ways of communicating between threads and coroutines. So I'm going to talk about the other side of threading, which is about threading for performance. So one of the, an example of something that we've tried to do at Facebook is when we have some work that has to happen after like a network request comes in, if we're able to parallelize it with the network request being out, then we can get some nice wins as far as being able to show stuff on the screen. One of the obvious problems with this is if the network is much faster than we might predict, and now you have the work in the background is not done by the time that you need it on the main thread. And there are a couple strategies that we can do to try to fix this. So one of them that kind of isn't the greatest is you can just redo the work. This actually is worse than not having done it in the background at all, because now you're actually competing with yourself on another thread, especially if that work might take out the same kinds of locks that the one on the main thread is doing. And another potential solution is to use something like futures. And futures are theoretically strictly better because you can start the work ahead of time, and then once you actually need the work, then you just block for the amount of time that's left for completing that work. So the code for converting something to a future is very simple. You might have something where you're like doing some expensive operation like generating a view model, and really you can just create a future task that the callable on that just calls generate. And this gives you the opportunity to run it on any thread and block on the result from any other thread. So unfortunately, I would love to say that this was like the magic solution to our problems, but it actually had a lot of issues, and we'll talk about them by talk about an experiment that we ended up running to try to highlight some of them. So for this experiment, we tried to first kind of simulate what might be happening on some of the phones that we're seeing bad behavior on. So we loaded up the CPU a little bit more by running some threads that are doing just throwaway work at a low priority. And then we wanted to set up this thing so that sometimes the main thread would be able to do the work, and then sometimes the background thread would get to it first, and the main thread has to block on the background thread. And because we want to see both cases, we came up with something where we just create the future, send it to the UI thread, send it to the background thread, and it's a race to see which one gets it. The first one who gets it gets to execute it, and the second one has to wait on the other one. So you basically have these two scenarios, one where the UI thread is executing, and one where the UI thread is waiting. And the code for the experiment is basically this. This is what we used. And again, it's also just doing throwaway work.
Now, before diving into the result of the experiments, the tool that we use to analyze the results is systrace. You might be familiar with it. It's a tool that gets used a lot to check performance of your Android application. Now, I want to focus on a feature of systrace that you might not be super aware of, or at least I wasn't in the beginning, which is if you zoom in on any of the instrumented blocks and you look at this highlighted line here, this actually gives you a lot of interesting information about the status of the thread. So the thread in this case, you see that there is a first block in light blue. That means that the thread has some work and it's ready to execute it. Then it goes into a green state. That means that the thread is actually executing some work. Whenever you see a white block, it means that the thread wanted to execute some work, but it couldn't because it was either locked or scheduled, like not scheduled to execute. No, sorry, this is just locked. Then you go into the ready state again, and then you start executing again. And it's especially interesting to notice that whenever you go into the ready state again, it's usually because someone unlocked you, which means that if you were trying to acquire a lock, and that lock was held by another thread, whenever that thread leaves that lock, frees that lock, you now get waken up by that thread, and systrace tells you which thread ID was waking you up, which means that now you can go and look at which thread was holding the lock while you were trying to run.
Cool. So when we ran this experiment and we were looking at systrace for it, we saw these very long blocks where the main thread was waiting for longer than we'd expect on this background work. And if you look carefully at the background thread, you'll notice that it's not, the top of it is not the color that we would really want. You can't see it maybe very well on the projector here, but that is a small little piece of green, and then the rest of it is blue. And this is because, this means that the thread, again, was able to run, but was not being scheduled by the scheduler. So this led us to realize that basically we have a priority inversion here where when we're blocking from the future on the main thread to the background thread is still running at its low priority, and it is not given anything special to make it run faster just because it's blocking the main thread. And on the other hand, the main thread is sitting there not able to do anything because it's waiting on this lock. So this leads us to kind of an important conclusion that you should be aware of if you're doing any sort of multi-threaded code with locks, which is that Android will not inherit priority for you, and you'll need to do it yourself. If you have any potential to possibly block on locks from the main thread to some sort of background thread, you really want to make sure that those background threads have the same priority as the main thread, or else you'll stall for longer than if you had done the work on the main thread.
So once we noticed this problem with futures, well, we went and we implemented a bright new feature. Sorry, terrible joke, I know. The idea here is pretty simple. Whenever a thread is about to lock on another thread that to get the result of a future, we check the priority of the thread that is about to lock, and if the priority that is currently executing the future has a lower priority, we raise the priority of that thread so that it now has the same priority of the thread locking on it. And whenever the thread has finished doing its work, we can lower it down the priority again to what it was before. Once we go and implement this new thread inheritance feature, we see that now our background thread gets to run pretty much all of the time, which is what we wanted in the first place. And of course, we went and implemented these primitives also for other things like locks. So we also have a priority inheriting lock, which again, whenever a thread is trying to acquire a lock, if the thread currently holding the lock is a lower priority, we raise the priority of that thread, and then we lower it down again once that thread has released the lock.
So Again, I would like to say that this like magically solved all of our problems and we don't have to think about this anymore, but there's actually a lot more complexity that is now under the covers, so I'm gonna talk to you about some of the other stuff that we uncovered after we implemented this. So I don't know about you, but my assumption was basically that if two threads have the same priority, then they're treated the same. And it turns out on Android that's not really true. And the reason for this is because of OEM optimizations. So an OEM can go and do things that, well, they're incentivized to try to make apps on their phone feel nicer than the same apps on other phones. So they try to come up with these ways to improve the feel of apps on their devices only. And two of these examples of these are priority boosting and core pinning. So priority boosting is pretty simple. It basically just means that they will go find the main thread of your application and go bump its priority. And sometimes they'll actually bump it to priorities that they won't allow other threads to take, so you can't even inherit that priority. The other one that I think is more interesting is core pinning. And so that goes to just the architecture of mobile devices. So a mobile device with multiple cores, each of these cores can run at different frequencies, which is just the clock speed. The reason you want to have them run at different frequencies is just for energy efficiency. If the phone's not in heavy use, you don't want to be giving it a bunch of power to keep the cores up at a high speed. And these cores are organized into things called power planes. So the power planes control what cores are at what frequency. So for example, you might have a phone that has 4 cores per power plane, and that basically means that you control the frequency of those cores as a unit. You have some phones that have power planes that have 2 cores, and then you have some phones that have power planes where each core is independently addressable and can have different frequencies. So the OEM optimization that happens here for some devices is that they will make sure that the UI thread is pinned to whatever the best core on the phone is, which means that even if your thread has the same priority as the main thread, it may get scheduled to one of these cores that's running at a much lower frequency. So you have the same priority, you're running code, but it's running at 0.8 gigahertz instead of like 2.1 gigahertz here, which I mean, can mean that your code is running about half the speed as it would have on the main thread. These OEM optimizations are very OEM dependent and constantly changing because they're always trying to innovate on like what they can do to make apps feel better. So it's not really something that you should really overfit your app to, but I think it's kind of interesting when you try to do stuff that's non-standard, you might get kind of screwed by things that the OEMs are doing under the hood.
So there is another thing that is not ideal about our priority inheritance future, because it is true that on one side we made the background thread go very fast, and it's doing the work that we needed it to do in the same time maybe that the UI thread would have taken. But I mean, if we go and check some of the cases where like this might be happening, we see that maybe the UI thread is actually waiting a pretty long time on this background thread. And while it's true that the UI thread would have probably done the same work on the UI thread itself, maybe the background thread has also some other work that it wants to do. And right now, we're not really optimizing for using our CPUs in the best way, because we have 2 pieces of work that we want to do, but we have one of our threads, actually the fastest, that is just sitting waiting for the other thread to complete all the heavy lifting. And the other thread that we might have boosted its priority, but it's still a background thread that is trying to do all the work. So is there any way that we can fix this? We were looking at like the data that came from production, and we decided that actually waiting on the UI thread was not the best possible solution. So we implemented a different way of doing this. Whenever the UI thread needs to get data from a background thread, and this background thread is running a feature, instead of simply locking, the UI thread can actually signal the background thread that that work is needed, and that actually the UI thread wants to take over that work instead of just leaving the background thread doing it. Which means that now the background thread, in theory, can transfer this work back, and the UI thread keeps finishing it. And the UI thread now has plenty of space to do other work. This is great, and this actually worked out very well for us, because it means that now we can really execute in parallel. And you might remember that when we started this presentation, we said that one of the ways to speed up your application is to make sure that all your threads are doing work like at the same time in parallel. Now, unfortunately, this is also not super easy to implement, because when we say work or when we have a future, it's just a very generic term. It's like the work might be a very big monolithic block of things that need to happen, and it might be stateful, and it might be very hard to like just transfer it from one thread to another. To be able to do this, you have to basically split your work into discrete pieces. And what happens is that every time you finish one of these discrete pieces, you go and check if another thread actually asked you to relieve control to it. And another thing that you have to make sure you do is you need to have very good ways of transferring the partial work between threads, because if the thread receiving the work has to do a bunch of operations just to understand where the work was left, this is actually not efficient and not worth it. Actually, there are a lot of very nice parallels between this and what you end up doing with things like coroutine. Coroutine as an API just like asks you to divide your work into a bunch of small pieces, when every coroutine can return a partial result to another coroutine, and that way like they can collaborate and use the CPUs in the best possible way.
Great. So to conclude, we saw how Android's threading abstractions are implemented with a common set of primitives and some of their parallels with coroutines. We saw some different trade-offs in queuing strategies. We saw how to understand what your threads are doing in systrace. And finally, we got a reminder to always measure your performance optimizations, because they might not actually improve things like you think that they will. So thank you very much.
Thank you.
I guess we'll have some questions.
I think we have plenty of time for questions. So, anyone?
Yeah, it's interesting stuff. I don't suppose you have any like example benchmarks we could look at for, you know, when you said about transferring the work and stuff.
Unfortunately, no. Like we have data from like what we did in production with our app. Do you remember any data specifically?
I mean, it's very hard to even simulate some of this stuff in benchmarks, because it's like whether something's good right now also depends even on like the breakdown of phones currently in the market. So it's also possible something is good now and then in a couple years isn't even good.
Actually, as an interesting side note, we were trying to simulate some of the core pinning stuff just to have some numbers to show in the talk. And it's pretty interesting because it turns out that whenever you have your phone plugged in, the CPUs are just like naturally going at a higher frequency on their own because you're charging. So it was very hard to get like any definitive numbers. We could get something, but it wasn't like polished enough to show. But yeah, so it's really hard to test these things.
Thank you for your talk. Do you invent some framework to break down work for pieces to transfer it?
So no, not really. I mean, just for some context, me and Andy both work in a team that works on UI frameworks at Facebook, and we work on this UI framework that is called Lito. And one of the features of the framework is that it can do layouts in a background thread. And which is why we went and implemented all these things, because sometimes we have a layout that is being computed on the background thread, but then suddenly we need it immediately on the UI thread because, well, we need to display something. So yeah, we have in Lito ways to split out our layout computation so that we can do this. But no, we don't have any generic API, unfortunately.
I mean, and the secret for us being able to do this is because the APIs that we tried to write are declarative, that they don't specify where you're supposed to do the work. It just specifies the work that you're supposed to do. And then we, as a constraint of using the framework, you have to be aware that your code can execute on any thread or it can execute multiple times. And by putting that constraint into the API and making the API declarative, that gives us the freedom to actually move stuff around and break it into chunks ourselves. But that's kind of specific to our framework.
Cool. Thank you, everyone.
Yeah, thank you.